These notes are going to go over mutation types, and we're going to talk about two specific types of mutations. We're going to talk about point mutations and frameshift mutations. Now, point mutations are also known as substitutions, when one base pair is replaced by another. And again, remember, mutations typically happen during DNA replication, which happens during both mitosis and meiosis. So in this case, we get one base pair that is then replaced by a different base pair. So here's my example. I've got a DNA sequence that reads CCTA, and when I have a point mutation, a base is then replaced with a different nucleotide. So C has been replaced with G. And in this case, I have 2 point mutations. So I have one happening here and I have one happening here. So the A has been substituted with a C. So you can have lots of point mutations or just one point mutation. But a point mutation is when one nucleotide or one base is being replaced by a different one. I'm going to be using the Fat Cat Ate the Rat to sort of give you an additional way of looking at how we look at mutations. So the fat cat ate the rat. Okay, and just like in genetics, when we're reading codons, we're going to read every 3 letters so that it reads the fat cat ate the rat. So we're always going to read every 3. So in the case of a silent mutation, which is what most point mutations are, so this is the most common type of point mutation, these mutations are when a base pair is substituted, but the change will still code for the same amino acid. So what you'll notice is a lot of our amino acids have 4 or 6 or 2 different codons that code for the same thing. And so it gives us a little bit of wiggle room when it comes to mistakes that are made. So let's say that I have a DNA mutation that replaces that T with a C. So instead of being TCT, it becomes TCC. Well, when I look at the corresponding mRNA sequence, my original one was AGA, which codes for arginine. Well, if I look at AGG, which is the mutated, it's a copy of that mutated code, I still get ARG. So if they both code for the same amino acid, I get the same amino acid sequence, which is going to result in the same protein being produced. Because if it's the same amino acid, then it's going to fold the same, and then it's going to function the same. So if you get the same amino acid sequence, it's going to result in a functional protein. So a functional, protein. And it's going to function in the same way it was intended to. You're not even going to notice that this mutation exists. Another type of mutation is a substitution. So when a base pair is substituted and a new codon codes for a different amino acid. So in this case, when I have a substitution, let's say I have TCT and then I have a mutation at this first position, so it becomes CCT, and the mRNA sequence that I would get would be AGA for this first one, and the mRNA sequence for CCT would be GGA. Well, then my corresponding amino acid in this case is going to be arginine for the first one, but glycine for the second one. So in this point mutation, I get a different amino acid. So if, let's say, I had a mutation similar to this in my fat cat ate the rat, let's say, I don't know, that I had a mutation here, and instead of having the T, I had a different letter. Instead of that C, I had a different letter. I have an H. Now it says, the fat hat ate the rat. Well, that sentence means something entirely different. So same thing for this mutation. If you switch out the amino acid, we now have a different amino acid sequence. And if you have a different amino acid sequence, that means that it will probably fold differently. And if it folds differently, the most likely scenario is that you make a non-functional protein. So again, that's the most likely when it comes to probability. So we'll probably fold differently. Most likely will be non-functional. There is a chance, however, that the amino acids are similar enough and it does fold the same and you get a functional protein. So you could still maybe have a chance that it folds and functions the same. Or there's a chance that you have some brand new function that never existed before. Which is the least likely scenario, is that you make a mistake and now you have some protein that does something new and that we've never seen before. But it's a total possibility. So our most likely is that it's non-functional. There's a chance that it could still be functional, or there's a chance that you could have some brand new function. But again, most likely it will be non-functional. So again, if I were looking at this, maybe I had a point mutation that says, thy fat cat ate the rat. So in that case, I still have this point mutation, but the sentence reads really similarly. And so maybe it's similar enough that it still functions okay. All right. So the last type of mutation that the last type of point mutation result that we can have is a premature stop. So in this case, you have a substitution. We're going to talk about insertions and deletions later. So you have a substitution and it forms a stop codon instead. And then if you hit a stop codon, basically what your instruction is to stop reading the rest of the codons. So it's basically like adding in a period. So let's say I get a mutation right here and instead it's replaced by a period. Now it says thy fat ka, and the sentence is over. You don't read anymore because you've told everybody to stop reading. So that's what happens with a premature stop. So if you get a mutation, let's say here's the mutation, right? And it's supposed to code for this mRNA strand, right? Which then codes for this sequence of amino acids, but instead, at this position right here, instead of coding for leucine, you code for stop. Then it stops reading everything that would have come afterwards. And so in this case, again, you're going to get a different amino acid sequence. In this case, a shorter amino acid sequence. And the most likely scenario for this is that it's going to fold differently and therefore most likely be non-functional. There's always a chance that maybe it still functions or maybe there's some brand new function, but the most likely scenario is you get a non-functional protein. All right, so those are all point mutations and things that can happen if you have a substitution or a point mutation that occurs. The next type of mutations we're going to talk about are frame shift mutations, and these shift what we call our reading frame. So again, we read every 3 letters, the fat cat ate, oh, that's an E, the rat. And if we have a frame shift mutation, that typically means that we have a mutation where you either insert or you delete a letter. So in these examples, you'll see right here, I have an insertion. In this one over here, this guy got deleted, and now my sequence is shorter. So it's easier to see when we're reading something that we're familiar with. So we're going to read every 3 here. The fat cat ate the rat. If you have a deletion, let's say anywhere that happens, I'm going to delete the F. What ends up happening is that every codon that I read afterwards is now shifted by 1. So now it reads the ats, atta, tet, her, at. Now every codon afterwards doesn't mean the same thing. It doesn't read the same. Or let's say you have, instead of a deletion, you have an insertion. So I insert a letter instead. I don't know, I'll insert one right here. We'll insert an I. So now it reads the fat cat iat eth era t. So every codon after the mutation now reads differently. So that's what a frame shift mutation is. So a frame shift is when you delete or insert and it shifts your reading frame, meaning that each codon following the mutation is now composed of a different 3 bases than it was prior to the mutation. So let's look at this example here. I have right here, it looks like a deletion. So it should read CCG, and in this case I just have a CG in the mutated version. So what ends up happening is that my original reading frame when I made my mRNA strand was CAC, CAG, GCU, UUG, and then UUG again. Or sorry, UGG. But now my reading frame right around here looks like it's going to change. So I still have the CAC, and I still have the CAG, but now because of that deletion, it's going to read CUU, UGU, GG, and so now everything that happened after the mutation, which occurred right around here, now each of these is different, right? It should be alanine, leucine, tryptophan. So the results here, well, we clearly end up with a different amino acid sequence, so every amino acid after, I should reword that, every codon after the frame shift mutation, after the insertion or deletion, reads differently. So therefore, I'm going to have a different amino acid sequence. And if you have a different amino acid sequence, likely that means that it will fold differently. And if it folds differently, it is most likely going to be non-functional. There is always a chance that it still functions, right? And there's a chance that maybe it has a brand new function, but the most likely scenario is that you make a non-functional protein. All right. A frame shift mutation where you get a whole codon that's deleted or inserted. So a whole new amino acid is added or one is missing from the amino acid sequence. So basically the idea here is we've shifted our frame by 3. So just like point mutations, you can have additional frame shift mutations. So let's say in this particular scenario of the fat cat ate the rat, that in this scenario, if you delete 2 of them, right, this is still just a regular frame shift mutation because every 3 still reads differently, right? So tika, tat, eth, era, t, right? So that still doesn't make any sense. But what if instead of 1 or 2 deletions, you had 3 deletions? So by some multiple of 3. Well, now it reads the cat ate the rat, which is sort of similar. It's just now missing amino acid. So that happens down here. So if you delete or insert multiples of 3, what you get is an additional or missing amino acid. So in this case, there is an addition that occurs right here. So after this particular amino acid, you get a bonus amino acid. But in this case, you still have a different amino acid sequence. And anytime your amino acid sequence is different, it will fold differently. And if it folds differently, then most likely it's going to be non-functional. There is always the chance that it does fold the same, just out of chance, and that it still functions, or that you get a brand new function. But the most likely scenario here is that it most likely is a non-functional protein. The last one is a premature stop. So just like in point mutations, you could have a frame shift mutation that results in a stop codon before you expected one. So again, in this case, we talked about substitution above, but an insertion or deletion that results in a stop codon before you would have originally gotten to a stop codon. And that just means that your amino acid sequence is going to be shorter. If your amino acid sequence is shorter, it will still likely fold differently. And if it is folding differently, it most likely will be non-functional. I do want to remind you that there is always a chance that it could fold and function the same. Not likely, but maybe. And there is always a chance that you get a brand new function. Okay, but these are rare and unlikely. All right, so you're going to use this information in order to answer some of the questions in this packet. We'll be looking at all the different types of mutations that exist and trying to identify them in class.